This is Tilmann Scheller from Samsung to give us a closer look at ARM code quality.
Yeah, hi. My name is Tilmann Scheller. I work in the Samsung open source group, and I'm here today to talk about ARM code quality. And let's get started with an overview. So first, a short introduction of just what this talk is all about. Then I will give just a very brief introduction about the ARM architecture. We will be looking at some ARM assembly later, so I just want to give a very brief introduction there. Then we will also look at some performance numbers. And in the case study, we will pick one benchmark and really have a look side by side, comparing Clang-generated code versus GCC-generated code, and look out for code optimization opportunities. So what is this all about? The goal here is to see where we are on ARM right now in terms of performance, especially compared versus GCC. And as mentioned before, we really want to go, have a detailed look at one of the benchmarks to see what kind of differences we have. And ultimately, we want to find out what we need to change in LVM or what we need to implement to get better performance. So let's get started with ARM. ARM is a classic RISC architecture, load store architecture. Three characteristics are the barrel shifter, the powerful indexed addressing modes, there's predication. So as you can see in the example here with the barrel shifter, you can so we are doing an addition here, and with the barrel shifter you can fold in an additional logical shift operation, so that allows you to create a little bit more compact code here and save an additional shift instruction. Same with the addressing modes. So this is a pre-indexed load with write back. So in addition to loading the value into R0, we also update the base register R1 with the new value, and this allows us to save an additional add instruction, which we would need to increment the base pointer. Predication, so every ARM instruction has a 4-bit predicate, and here we can see a load predicated on equals, and this is a way, for example, if you have an if statement with a relatively short body, then it makes sense to just predicate the instructions rather than having explicit branch instructions, and just avoid this overhead. So the ARM architecture actually has been around for quite some time. ARM v1 was introduced in 1985. So when we talk about ARM, it's actually a family of instruction sets. So there's which evolved over time. So there's the original 32-bit ARM instruction set. Then at some point, thumb was introduced, which is a 16-bit subset. And at some point, also the thumb2 instruction set was introduced, which tries to give you the best of both worlds, which is performance similar to what you get with the original ARM instruction set, but code density closer to what you would get with thumb. And thumb2 is actually a variable length instruction set, so instructions can be either 16 or 32-bit long. And the focus here is on thumb2, because this is really, if you target 32-bit ARM today, that's what you compile for. And the base instruction set doesn't really have any support for native floating point or vector instructions, and that's where we have VFP and Neon. And if you want native support, you can implement that on your chip. In terms of registers, we have 16 general purpose registers. This includes the program counter and stack pointer, so the number of actually usable registers is a little bit lower. If you have VFP support or Neon, then you have an additional floating point register file, And this is shared between the two extensions. And on thumb 2, to preserve instruction size, there is no explicit field for conditional execution. However, you have the IT, which stands for if-then instruction, which allows you to predicate up to 4 consecutive instructions on the predicate you specify or the inverse of it. And I have a small example here where we have just this if condition, then we have the if-then instruction, and then we have 2 moves, one predicated on equals, the other one predicated on not equals. And that's a very compact way just to get this if statement mapped to ARM machine code. So let's move on to performance. What kind of hardware are we doing the measurements on? We've been using Arndale Octaboard. This is just a standard 32-bit big little system. So it's a quad A15 with a quad A7. We only really care about the A15s here. And they are clocked at 1.8 gigahertz. The board has 2 gigabytes of RAM and is running Ubuntu Linux. And if you just take the board, do some benchmark runs, then what you notice is that you get quite some variation in the benchmark results. So it makes sense to do some preparations to get more stable results. So this includes obvious things like disabling services you don't need, disabling any cron jobs you have. It's a good idea to turn off frequency scaling to don't have any variation there. Another thing, ASLR is a good feature for security, but for benchmarks, because benchmarks which rely on the memory layout or something, they can really get quite some variance there. And what also makes a lot of sense is that you just turn off all cores except one where you run all the benchmarks on. And this really, in my experience, that is what helps the most to get more stable numbers. And if your board has enough RAM or your benchmark is small enough, it also makes sense to just put it into a RAM disk. That way you can eliminate any I/O latency. And static builds is another thing. That way you can really get self-contained binaries without any dependencies on any system libraries, and that makes it a little bit easier. So let's have a look at some current numbers. So this is SPEC 2K compiled for A15, and Neon turned on at 03 level. And so this is just spec in, so I'm only focusing on integer code here. And we are comparing Clang build, which is about, is a trunk build about 2 weeks old. And we are comparing against the Linaro GCC 4.8 and just a vanilla GCC 4.9. And let's have a look at some relative numbers so we can see a little bit more details here. A positive percentage means GCC is faster. Negative means Clang is faster. So you can see we're still, GCC still wins most of the benchmarks on ARM, 32-bit ARM. But there are also benchmarks like Crafty and Parser where we are significantly better. There are really just 3 benchmarks where GCC is significantly faster. So Perl, Eon, Gap, and VPR. Gap is kind of special because it relies on wrap amount semantics for signed integer overflow. So, and technically that's undefined behavior. And in fact, if you compile it with Clang, you get a binary which doesn't work. So you have to specify the -f wrap-v flag so that you get a proper wraparound semantics. For the remainder of the talk, I want to focus on VPR because it has some properties which make it a good candidate for, just looking at it in a presentation like this. What's VPR? VPR stands for versatile place and route. This is a FPGA circuit placement and routing application. Internally, it is doing, for the placement is done by doing a random initial placement and then just refining it with simulated annealing. The routing is done just with standard graph algorithms, in particular a variant of the classic Dijkstra algorithm. And in SPEC, we actually have two invocations of VPR. So there's one invocation for the placement and the second one for the routing. And we see the higher slowdown in the routing. So that's what we want to focus on. And another thing, VPR is open source. So I actually can show some C source code here, which would not be possible if I take it directly from SPEC. And the version of VPR I'm using here, the open source version, is not identical, but the function we are going to have a closer look at is in fact identical to SPEC. So yeah, that solves this problem. I'm actually measuring against GCC 4.8 because it generates better code. So there's as you saw earlier on the chart, is like a 5% regression on the GCC side for VPR. I'm building with the LLVM vectorizer turned off. That also regresses like 1% or 2%. And I also turned off inlining so that we can get a clearer picture of the performance profile, just to see which functions are really important here. Ultimately, of course, we want to optimize the build with inlining turned on, but this is just to get a more accurate picture. And in fact, it's very clear. So there are just three functions here which dominate the runtime. Almost 80% of the time, or 83% of the time is spent in the top three functions, and almost half of the time is just spent in a single function called getHeapHead. And this is the function we want to have a closer look at. First, a couple of metrics. Clang is generating more compact code for getHeapHead. So we have 53 instructions versus 69 instructions. If you look at the dynamic instruction count, the whole run takes between 77 and 79 billion instructions. getHeapHead takes up about 35 to 37 billion instructions. And as you can see, GCC actually executes 2 billion instructions more than Clang, but the GCC build still finishes in 10% less time. So that's a good example why if you just look at the instruction count, it can give you the wrong picture if you want to analyze the performance. Here's the source code of getHeapHead. Can everyone see this from the back? Or so getHeapHead basically for the routing, because it's using the Dijkstra algorithm, and the Dijkstra algorithm uses a priority queue, and this is implemented with a heap data structure here. A heap is basically a tree-like data structure where you have, in our case, you always have the smallest element at the root, and you have a heap property which ensures that the children always have a lower value than their parent, and that way you get a partially ordering across your heap. And what getHeapHead is doing, it just takes the smallest element from the heap, and then it takes the last element on the heap, moves it to the front or to the root, and then just walks through the whole heap, and well, not the whole heap, but through the heap, and makes sure the heap property is ensured again by switching individual heap elements. So in terms of variables, we have this just this dynamically sized array of pointers to struct as heap elements. So those are our actually heap elements. We have a member here with a floating point value which indicates the cost. And we have a variable called heap tail, which just points at the first unused slot on the heap. So it's kind of the end. And the function, what is it doing? In the beginning, there's just a check for an empty heap. So the heap should never be empty if you call get heap head. Then it just fetches the root element and takes the element from the end of the heap, moves it to the front, and then we have this while loop where we just walk over the heap and make sure the heap property is enforced again. And that's pretty much it. So it's just fits on one slide, and this is what we get if we compile this with Clang. And I've split it up into 3 parts so that we can look at them side by side with GCC. And this is what we get with GCC, a little bit more code, as mentioned before. And yeah, let's start with the first part. So this is where we have the check for the empty heap, fetch the smallest element, and move the last element from the heap to the front. And the first thing we see here is that in the prologue, where we save the non-volatile registers, we can see that Clang is generating a push instruction while GCC is generating a sequence of paired stores. So the question is, why is GCC doing that? And the answer is, on Cortex A15, you actually get better performance if you use paired stores rather than a store multiple instruction. So that's the reason why GCC is doing that. Another thing, so we are loading heap tail and heap, and they are both adjacent in memory. Yes?
I think that the push is just not generated. It's just a coincidence. Don't read anything yet.
Okay.
No, it's a misoptimization. It's shorter there. On Clang side, it's short. GC should have a generated.
You think it's, I haven't really analyzed the performance there by hand modifying it, but that's... Okay. So, okay, let's move on. So we have those 2 adjacent values here, and GCC is combining them into, it sees that you can fold them into a single paired load. And I don't know why LVM is not getting this. I would think that the load store combiner could actually do this. Need to have a closer look there. So the next part, this is where we enter the while loop. We have 2 if conditions here where we check cost members at I2 and I2 plus 1. So if you just look at this, you would think, okay, I see cost dereferenced 4 times. There must be 4 loads. But actually, we have a redundancy there. So because in the first if expression, we are loading the cost member at I2 plus 1 and I2, no matter what kind of result we get here, and it doesn't really matter whether I2 gets incremented or not, we will always have already the value which we need to get here, because there's just no intervening stores or anything. So it is sufficient to have 3 loads here. And in fact, that's what GCC is seeing, and is generating a move instead, or a couple of moves actually. And also, if you look at the performance profile and you look on the per instruction profiling information, those loads into the Neon register file, they show up as very hot. So I think this is one optimization which is quite important for VPR. Another thing here, so here we have Clang is reloading the pointer to the heap again. This is really a redundant load. There's no need to do it. And GCC, in fact, just loads it once, keeps it alive across the whole function. And Clang, for some reason, thinks the value might get clobbered and reloads it again. So this is already the third part. And this is basically the second part of the while loop where we exchange elements on the heap if there's a need to. And here we can see another redundant load of the heap pointer. And so this is actually not really a performance optimization here, which is GCC is doing. So on the right-hand side, so we are checking whether R1 contains the value -1. And this is a 32-bit instruction. We have the suffix .w, which stands for wide. So this code sequence is actually 6 bytes long. The branch is a 16-bit instruction. And on the right, we just have an addition and the branch not equals. And the add is a 16-bit instruction. So we actually save 2 bytes on the right side. And yeah, this is a perfectly valid transformation to make. If you just think about it, you have -1, you add 1, you get 0. 0 means the program status register will get the 0 flag, and that's just what we're checking here for. So for values which fit into the immediate of this add instruction, this is a nice code size optimization. And yeah, so just recap what kind of optimization opportunities did we see here. Probably the most important one is the redundant load in the if statements. Then we have the 2 redundant loads of the heap variable, which could be eliminated. And on function entry, where GCC is combining the 2 loads into a single paired load, that's definitely something interesting. And yeah, emitting paired loads and stores rather than load and store multiple instruction, that's something to think about. I haven't really measured it, but I guess it's faster. Code size, yeah, I think that's a nice optimization to have. Okay, so summary. There's ongoing work to implement those optimizations, so I started working on eliminating the redundant load and already submitted a patch, still trying to find a better way to do this. So I've implemented it in inst combine, but it should be implemented in the GVN pass because that's where we do a lot of redundant load optimizations. So that's something I'm working on. And this is a middle-end optimization, so there are other targets where other targets which benefit from this as well. I know that on AR64 this also helps. In general, LLVM is getting close to be on par. So actually, I forgot to mention this. So we are GCC is about 3% faster on average with the SPEC geometric mean. So that's not too bad. I think that was much worse. I think a lot of the AH64 optimization work had an influence on that as well. And yeah, they are just really just 4 benchmarks where we are significantly worse than GCC. And yeah, overall code quality is definitely very high. It's just getting those small things worked out. And yeah, okay. that's it.
Let's thank our speaker. Questions?
So just another thing, so we are growing the Samsung open source group, and we are we are looking for more people in the LLVM community, and we are hiring both in the US and in Europe, pretty much worldwide. So if you're interested to hear more about that, or just get in touch with me either by email or talk to me here, I can give you more details.
So in the beginning, you say that you disable all the CPUs except one.
Yep.
We came in a different way. We just enabled 2 of them, and one of and put the affinity on the second one, and let the kernel and everything in the first one.
Yep.
Did you try to do that? Did you?
I tried this as well. So I used there's some kernel option where you can just reserve or can tell the scheduler to ignore one of the CPU and then manually schedule SPEC over there. Yeah. But I did not really see a real improvement in stability of the numbers. So I don't really know why. So maybe I just picked the wrong core and they were sharing the same cache or something. Or it's just some bug in the Linux kernel. I don't really know, and I haven't really spent time investigating why.
Yeah, we done this because we thought it was a good idea, not because we actually seen anything different. It's just wanting to see if you've seen anything different. You didn't.
Yeah, no, in practice it didn't really improve the results. Yep.
For GVN and change, did you verify it removed the redundant load from VPR?
Yeah.
It was successful then?
Yeah, so it removed it, but the thing is, some other stuff gets introduced. So I was not actually seeing a performance improvement because, it's just, I think it's like 3 or 4 instructions getting introduced, which is a redundant it instruction. There's an additional floating point compare, and I think that slows down things a lot. So it felt kind of like 1 step forward, 2 steps back, but I need to find a way how to get rid of those redundancies as well.
All right.
Any additional questions? Let's thank our speaker.